Bismillahirrahmanirrahim. Inshallah, today we'll talk about how a cell secures energy for itself. Specifically, we shall talk about photosynthesis, which is one of the most fundamental biochemical phenomena for living things. So, as you know, photosynthesis is a process of plants taking carbon dioxide from the air, combining it with water, and with the help of light and chlorophyll, producing glucose and oxygen. Now, this equation is basic and fundamental, and you should know this. So if somebody were to ask you, for example, what is photosynthesis? Photosynthesis is a process by which plants take carbon dioxide and water, and with the help of light and chlorophyll, they produce sugar, or glucose specifically, and oxygen. The glucose is a carbohydrate, and the word carbohydrate refers to the carbon molecules being hydrated, so to speak, simplistically speaking. So, carbohydrate. The molecular formula for carbohydrate is C6H12O6, which you should also know. C6H12O6, just like you should know H2 is water, CO2 is carbon dioxide. You should also know that C6H12O6 is glucose. In addition to this, what's not written in this equation is that energy is also produced in other forms. In other words, if you should add another plus here and some energy to complete this reaction. So this is the overall view, the big picture of photosynthesis. Now, photosynthesis occurs in autotrophs only. In other words, you and I obviously don't do photosynthesis, and that's why we're not green and we don't have leaves and absorbing light. So we don't do photosynthesis. Only autotrophs do, primary producers do. And they use light to make energy-rich compounds. This is a more comprehensive statement, because glucose is only one form in which the plant stores the energy that it captures from the sun. So glucose is one way the plant stores the energy that it captures from the sun. And also, putting in plain English, plants use sun's energy to manufacture food via photosynthesis. So here's a cartoon representation of the same: carbon dioxide from the air, water from the ground. So when you water plants, you're actually putting the water in there so they can do their photosynthesis. The byproduct of photosynthesis is oxygen that you and I breathe, and carbohydrates. Okay? Here's another representation of the same carbon dioxide plus water. And this is a balanced equation, so you need 6 carbon dioxide, 6 water to produce the glucose. This is an incomplete cartoon picture. It's still a simplified version of glucose and oxygen molecules. Now, when we say stored energy, what do we mean by that? So, see, to carry out cellular processes, to do anything, requires energy. So when we say you don't have energy, or something doesn't have energy, they mean that they are unable to carry on the biochemical processes that they need to do. To do any biochemical processes, not any, but most biochemical processes, you need some energy. And this energy is stored in the body in several ways. One of the ways is in glucose. Now, glucose is a storage form of energy, because understand that plant can't do photosynthesis 24 hours a day, because how are you going to do photosynthesis when it's dark, there's no sunlight? So what do plants do for that nearly 1/2 of the day where there's no sunlight? Because they're dependent on energy on a minute-to-minute basis. Just like people can suffocate and if they don't have oxygen for a few minutes and die, because oxygen is essentially needed for survival and getting energy. So survival is really a minute-to-minute basis. So for all the time that there's no light, the plant needs to have backup storage of energy. So the glucose is in fact that backup storage of energy. So a plant makes some of the energy and stores it as glucose, but it also makes a lot of energy in the form of ATP. ATP and glucose have the same function in a way. They are stored form of energy. What energy? The energy they ultimately get from the sun. So that energy that they ultimately get from the sun is stored in these molecules. We'll talk about what that means to store the energy. This is a structure of ATP. ATP stands for adenosine triphosphate. Adenosine triphosphate. ATP is like a nucleic acid, like the basic building blocks of DNA, RNA, basic structures just like that, which is quite intriguing in itself. But nevertheless, so ATP, it has three parts to it. It has a sugar ring, just like nucleotides of DNA, RNA, and it has this base, which is adenine, okay, just like the nucleotide. So adenine and this sugar base, and it has three phosphate groups attached in the end. Okay, that's why it's called adenosine triphosphate, which you also need to know. So ATP is short for adenosine triphosphate. If you look at adenosine triphosphate, the 3-phosphate, this third phosphate bond is a high energy bond. In other words, if you need to do some chemical reaction, and the chemical reaction can occur if it had a little extra energy. See, when you cook food, the reason you put them on the stove is because the heat provides energy for the chemical reactions to occur when you cook food. Okay, so ATP is like the heat that you're providing from the stove. It gives a little extra energy. Those chemicals, the reactions that are occurring on the stove, they would occur naturally, but it's such extreme low rate that you would have to wait several years to have the breakfast ready. But giving the energy gives it the extra energy, allows that reaction to occur quickly. So that's also a very simplistic representation of the scenario, but that's basically what it is. So ATP has energy that it can give to other compounds to carry on the reactions, and that energy is stored in this bond. Okay, that energy is stored in this bond. So you have to also know that this bond, this last bond between phosphate, that's where the energy is stored in ATP. And reactions where ATP is used to as the energy source, this bond is broken, and that breaking of that bond gives energy that you can use to carry out reactions. So now, as a summary, when plants do photosynthesis, they capture sunlight's energy and they save it in different forms. Two of the most important forms are glucose. Now, glucose is a stored form of energy for a time that the plant is unable to do photosynthesis and make ATP, which is an immediate source of energy for plants. It's like, cash money, so to speak. So, and then when the plant, at nighttime, for example, the plant will break the glucose down into ATP and molecules like that provide energy. So these are the two most fundamental stored forms of energy. That's how plant stores the energy. Here's another example of ATP. Now, I emphasize this because you have to know actually what the goal here is for the plants. If you don't, the plant is to capture the energy and store it in these type of molecules, glucose and ATP. Here's again is the adenosine triphosphate molecule with a 3-phosphate group and the ribose base and the nitrogenous base over here, the adenine. Now, here's another picture of ATP because it's just that important. So ATP is like cash money. When plant do photosynthesis, they make ATP, and they use the ATP for minute-to-minute basis for chemical reactions. But as I said, they can't do photosynthesis at nighttime, so they have stored form energy in the glucose, and they use that, or in wintertime in stored form, etc. Where in wintertime you don't have as much sunlight. So they use the stored form of energy. But ATP is like cash. It's like you can go there and just give it to carry on the reaction adenosine triphosphate, 3-phosphate, triphosphate. Now, what do we mean by storing that energy? So as I suggested, this energy stored in this bond, okay? Energy stored in this bond, the 3rd phosphate bond. What does that mean, to store energy in that bond? I should try to explain it to you. Now, here's a cartoon representation of the sodium atom. A cartoon representation of the sodium atom. Now, all those little dots that you see are electrons going about the sodium. This is, of course, a very simplified version of, and in the middle is the nucleus. All these electrons are not the same. Okay, the electrons that are closer to the nucleus, they don't have as much energy compared to electrons that are farther from the nucleus, which have more energy. So electrons that are farther from the nucleus, okay, have more energy. Okay, and how do you take an electron that has low energy and turn it into high energy? Okay, how do you take an electron that has low energy, convert it to high energy? Now, we know they have low energy. So low energy because one form of energy is kinetic energy. They move faster. So now, how do you convert a low energy electron to a high energy electron? You give it energy. Okay, that's what you're doing when you're heating things. Okay, and it's energy comes in different forms. One of the forms energy comes is light. Now, light is actually a particle and wave, right? So it has energy. In fact, if you can use sunlight to burn, the magnifying glass to burn paper, right? So light has energy. If a light particle, which has energy, were to go in there and hit that electron, it combines with the electron. It combines with the electron. Light part combines with the electron, and it gives the electron more energy. It has more kinetic energy, like moves faster. Okay, so when light strikes electron, it moves faster. It becomes part of the electron. Not all electrons are created the same. Okay, it's not like they're different. It's like saying all Indians look the same, or all Chinese look the same. No, they're not. They're very different. There are electrons that have low energy, electrons that have higher energy, etc. So that's the idea. Now, if you have this electron, for example, this electron is in the first orbital. It's not nearly as much as energy as the second orbital, and the third orbital, and the fourth orbital. See, when the light strikes the electron, it gains energy and goes to the next higher level. Now, the interesting thing about this phenomenon, on the side note, is that when the light strikes, see, it's keep going up. When the light strikes the electron, it goes in the higher orbital. Light is particulate matter, and therefore the jumps are always the same. They're always the same. In other words, there's no orbital between these two, because from here to here is a difference between one packet of light, so to speak. From here to here is another packet of light, and the jumps are always the same. It's one of the more beautiful phenomena of chemistry to explain this. See, when the light strikes it, the electron gets energized. Now, so we said, how does the photosynthesis store energy? So what happens is, photosynthesis is a process where these electrons are converted from low energy to high energy, like this, and then those electrons are used, and then they go into ATP. These electrons are transferred to ATP, and if you recall, it's the outermost highest energy electrons that are involved in chemical reactions. So you're making these electrons that have high energy electrons outermost valence electrons. Essentially, that's what you're doing. You're giving valence electrons. You're creating valence electrons, and you're storing those valence electrons in the form of ATP. And that's what we mean by storing those electrons in those forms. And if you recall, it is the valence electrons that determine how a chemical reaction is going to occur, because they have high energy. And if you understand that, which I hope you do, the process becomes very beautiful in how remarkably elegant it is in doing this process. So here's again, this tells us when electron can gain energy, go to higher orbital level, and it can lose energy and higher. So when things cool, they actually can also give off light. So when things get heated and cool, that's when they change color. It's just like the stove metal changes color because of light, and that's all really because electrons going up and down in different orbitals. And when they go down in the orbitals, they release light. Okay. So here's another representation, all to suggest to you that not electrons are not created equal. Some have more energy than others. Now, here's what happens. Now we're going to talk about photosynthesis proper, okay? So the beginning of photosynthesis occurs when light strikes an electron and it goes to a higher energy level. And then, see what happens is, there's another molecule, and this molecule is known as the electron acceptor, okay? Watch what happens. So the light strikes the electron. Now this electron, sometimes light strikes the electron so much, and the electron is so excited it escapes the nucleus, right? It wants to just it escapes like too much caffeine. So when it strikes it, escapes the nucleus, there are other molecules that are ready to capture. Why? What do you mean ready to capture? I mean they have affinity for these electrons, so they capture the electrons. So, okay. So now, what do you think is the ultimate fate of that electron? Inshallah, yes. If you said that goes to in storage form ATP and glucose, that would be the awesome, beautiful answer. And that's exactly what happens, because you take an atom and then you convert the electrons, and then you get that electron, and then this electron acceptor is just like a taxi. It's ultimately going to take those electrons to where it needs to go. So this is the first step. The first step is the light strikes an atom, excites an electron, that electron is released and is accepted. Okay, so photon, electron goes to light, and light is a thing, just like anything, goes to electron, and the electron captures, becomes part of the electron, and the electron is excited. Okay, just like this. Ta-da, it's higher energy electron. Okay, now photosynthesis is divided into two parts. Okay, we should talk about the first part here, and then we'll talk about the second part inshallah next time. Photosynthesis as a process divided into two parts. The first part is called light dependent part. The second part is called light independent part, sometimes called the dark reactions. You know, it's really, but more appropriately is light independent reaction. So the first part is light dependent. In other words, sunlight is an integral part of this first half of the photosynthesis. If there's no sunlight, the first half is just is not happening. It's a shop closed, so to speak. So because it requires sunlight, and this part is where the sunlight excites the electron. Okay. And light and water gives oxygen and electron. Okay? And then to take the electron, what do you do with it? And from that electron, you generate ATP molecule and NADPH molecules. This is another cash molecule. It's like, you know, it's like a dollar bill, it's like a $5 bill type thing. Okay? So ATP and NADPH, those you have to know. So that's the first part. The first part is taking light, exciting the electron, and using light and water to make the excited electron and oxygen, and generating ATP and NADPH from those. Now that's cash, if you remind you. But you can only do this when there's sunlight. But then there's second part. This is called light independent. It's like packaging, okay? This means this part does not require sunlight. This is the part when you take the ATP and store it in the form of glucose for later use. So this is where it happens. Okay, as you know, all of photosynthesis occurs in the chloroplast. in the chloroplast, there are these thylakoids. All the action is in thylakoid membranes over here. So this is a cartoon representation of a chloroplast, and this is a thylakoid. Okay. Now, the light part of the reaction occurs on these thylakoid membranes. The light strikes over there, that's where the chlorophyll is, and the water is needed for this part of the reaction. And then oxygen is a byproduct of this reaction. So the first part has light and water as the ingredient and produces the oxygen. Now this part generates two things. It generates ATP and NADPH. That's cash. Now if you need the ATP, you can use it. This can go to the rest of the cell. This can go to the rest of the cell and use it. But some of it is converted into glucose for later use. So you can use it, for whatever need, and then some of it is converted to glucose. So during the daytime, plant is working very hard to make all the ATP it needs for its current needs, plus also a bunch more so it can save it for later use. And converting ATP and NADPH into glucose is the second part of photosynthesis. And this requires carbon dioxide. Okay? So the first part is taking light and water and producing ATP and NADPH, and oxygen is the byproduct. And the second part is carbon dioxide, taking that as an ingredient and combining with ATP and NADPH to produce glucose. This is called the light stage, sometimes called the dark stage, this part, light dependent stage and light independent stage. Here's the chloroplast. We have seen this before. So those are the thylakoids. That's where photosynthesis occurs. And then outside the thylakoid is the stroma. Okay. Now here, so what's the big deal about chlorophyll? What's the big deal? So chlorophyll is on the thylakoids. See, chlorophyll is all on the thylakoids. Okay. Now this is where the light independent reactions, the dark reactions, so to speak, occur in the stroma outside the thylakoid. But thylakoids is where all the chlorophyll is. Now, what's the big deal about chlorophyll? The chlorophyll is a curiously interesting molecule, and it's kind of like stored over here, like little tiny things here, and inside of it is an atom that likes to give off electrons. Okay, but only if the light strikes it in a particular manner. So all the chlorophyll is, and there are like millions of them in every little one of this, is a carpet. So the thylakoid membrane is basically a carpet of laid out chlorophyll molecules in the membrane. And chlorophyll molecules is special because in the middle of it is a metal ion, it's an atom that likes to give off electrons, and basically has carpeted these atoms over there, ready to give off their electrons if they are struck with light. And not all atoms, obviously, are like that, right? And so they won't. Not all atoms have the same ability to capture light and give off their electrons. But here, it takes all the atoms are lined up. So when the light does strike, it releases electrons, and these electrons, they bounce from one atom to another atom until they're captured by the electron acceptor. Okay, so once the electron gets excited, it's looking for a resting place, so to speak, and the resting place for electron is the electron acceptor, which has an affinity for electrons. So now, so when the light strikes here, right, and electrons are released. Okay, and those electrons are accepted by the electron acceptor. Now, if you can imagine then, all these electrons are being released, right? After a while, these atoms are going to be like electron naked or something like that. You know what I'm saying? All the electrons are going to be gone, right? So what's going to happen then is that what? So those electrons have to be replaced somehow. Now they have to be replaced by not high energy electron, but the low energy electron, and those are dime a dozen. Low energy electrons, are very common. So these electrons that are released, they have to be replaced by some other electrons, otherwise you won't have any more electrons to excite after a while, right? They all leave. So those electrons have to be replaced. And who replaces them? Well, a very common substance in nature, right? The earth is like, most of the earth is water, right? So water is important for the first part, because water, okay, the H2O molecule, is the source of those replacement of those electrons. The most abundant substance in the world is like the engine for the photosynthesis, the fuel for photosynthesis. Okay, so the photosynthesis reaction is commonly written as carbon dioxide plus water equals glucose. It probably should be written as water plus carbon dioxide, because water comes into the story first. Because water is the electron donor, the molecule that donates the electrons that have been excited and released. So the electrons that are lost are replaced by water. Okay? Now look what happens over here. See? Light strikes over here, and this electron are released. Okay, now these are high energy electrons. And then those electrons have to be replaced. So here's water. Okay? It gives up 2 electrons. As a result, 2 hydrogen ions are produced and oxygen molecules. Now, look at these 2 hydrogen ions. The hydrogen atom has 1 proton and 1 electron. If it loses the electron, okay, it becomes a hydrogen ion. It's really the hydrogen ion in the water molecule that gives up. It's a hydrogen atom in the water molecule that gives up the electron. Each hydrogen atom has 1 electron, so 2 electrons are given here. So for every water molecule that's broken down, there are 2 electrons that are given to the chlorophyll molecules that have lost the electrons. Now look, think about this for a second. Hydrogen atom is the most basic of all atoms, and it is the driving force for photosynthesis. It is one that gives up its electron to replace the electrons that have been lost. The most basic atom gives up its electron. Now you gotta have respect for the hydrogen atom, right? You think it's a little lonely atom, but no, it's the atom that's driving the whole process. Okay. Now when the 2 hydrogen ions are created, okay, when oxygen molecules when 2 water molecules are broken, the 2 oxygen molecules from 2 different oxygens get together. Okay? So the water is the donator. Then you say, where does the excited electron go? Now this is really beautiful. Where does it go? Okay. So here's the thylakoid. Okay. So all of the reaction is happening on the membrane. Okay. Now look at this. Now we're going to talk about what's happening in the membrane in detail. It's kind of scary when you first look at it, but it's really quite beautiful. It's like a play of electrons. It's like a musical chair of electrons. All of the chlorophyll, etc., that is here, as I said, is carpeted over here in the membrane. But along there are these other big protein molecules. They're called photosystems. They're huge, sort of the biggest protein molecules. They're called photosystems. They're photosystem 1 and photosystem 2. There's only 2, all right? So it's not that big of a deal. So photosystem 1, photosystem 2. They are huge protein complexes, and there are a whole bunch of other proteins. Now, they're the one they play musical chair with the electrons, so to speak. Okay, it's kind of cool if you understand it. Okay, so this is what happens. So you take the photon over here, all right? You take the photon, light strikes it, and that becomes a high energy electron. Now what happens is, see, that energy in the photon, in the electron, is used to create ATP. But as that happens, it transfers its energy, and then you create ATP. The electron loses its energy, right? And then the light strikes again 2 times, and it gives them more energy again. So in one cycle, the light striking occurs 2 times. Okay, 1 time here, 1 time here, light here, and light here. And the second time, when the electron gets more energy, that's used to make NADP, the other cash molecule. So ATP is generated from here, ATP is generated here. Okay? Now, very important thing I like to suggest here. So the light reactions occur on the thylakoid. The light independent reactions, the dark reactions, occur in the stroma. They occur outside of the thylakoid. That makes sense because thylakoids are really only like chlorophyll, mills basically. They're just like boatloads of chlorophyll stacked on membranes, right? So that's where the light reactions occur. The light independent reaction, the dark reactions, which is called Calvin cycle, occurs in the stroma of the chloroplast. And the light reactions make the cash crop, so to speak, ATP and ADP. Some of it is used for daily activities, and then it goes to this cycle, this part of the photosynthesis, if it wants to be converted into sugar. Look at this. It should make intuitive sense to you. Water comes here in the first part, and hydrogen atom donates electrons. Oxygen is made into oxygen here. So 2 water molecules break, releasing 4 electrons total, and two of those oxygens get together into making them a very stable oxygen molecule, which just diffuses out of the plant and which we breathe. Okay, so this should make complete sense to you. From water molecule, oxygen over here, and this part of it should make complete sense to you. Okay, and I hope it does. So this is just a chlorophyll molecule, as I said. Now, you can pause at any time during this and just take a breather or whatever it takes. But you gotta know photosynthesis is a very beautiful phenomenon. And I would request you if you take the time to understand this, you can appreciate nature in general, I think, much more. So now look what happens, okay? The light strikes over here, and this electron, okay, it bounces around. It eventually is captured by the electron acceptor, okay? Now, the cell is so smart. Allah created this so beautifully, okay? You use the electrons to do some work, and it's very ingenious. See what happens. Watch. So now you have this supercharged electrons, right? So now you have supercharged electrons. So there's carrier proteins that do this. They take the electrons way up there. So here's them. They're collected over there. Okay? Once they're collected over there in the electron acceptor, okay, those electrons carried closer to this part of the membrane. Okay? And then, as we already said, water replaces those 2 electrons. The supercharged electrons have to be replaced, right? Because otherwise you will have no more electrons left in there to excite. So those supercharged electrons are replaced by water. Okay, that's that. We got that. Now look what happens. Now, here's these electrons now, right? Now, you know positive charges and negative charges, they attract each other, right? So here's these negative electrons over here, correct? And here's this hydrogen ions over here. What do you think the hydrogen ions want to do? Okay? Now, these hydrogen ions are naturally are going to be attracted towards those electrons. They're right there, sitting right there. It's like, oh my God, those are not my electrons, but those are some supercharged electrons. I wish I could have those, but I tell you what. Do you think that hydrogen ion is going to capture those 2 high energy electrons? No way. So 1 proton, those electrons are way too energetic for that 1 proton. They're not going to stick around. But what happens? But there's this electrical attraction between the negative charges and positive charges. So hydrogen ions is going to naturally want to go that way, right? So they want to go this way, right? Oh, that's exactly what this protein has in mind, so to speak. Is going to attract those hydrogen ions. Okay, well, look what happens. Okay. Look over here. Oh, this picture is a complicated looking picture, okay? Complicated looking picture, but just observe over here. Look over here, light striking here is called photosystem 2, which occurs first in our story, but it's kind of weird the way they named it. I don't know how, maybe that's how they discovered it, but photosystem 2 is the first one that's involved. Look, light striking over here. Just look over here on the bottom left, okay? Water coming in. See that? Giving all those hydrogen ions. and oxygen leaving. Where's oxygen leaving? It's going up into the air, atmosphere, so then I can breathe it. It's just diffusing out of the cell. Okay? Look, all these hydrogen ions produced. Look at all these hydrogen ions produced. What are they going to do? It's going to be a riot. It's going to be a lot of hydrogen ions in the cell after a while. Okay? Now look, the electrons go over here, right? Electrons are all over here, right? Okay. Now what's going to happen is that now you're making all these hydrogen ions, right? Now there are hydrogen ions over there. Now, electrons, so the hydrogen ions outside will tell you where do they come from. But this is really critical. Now look, there's electrons over here. There's electrons over here, right? And I said these hydrogen ions are attracted to over there, right? Okay. But these electrons are closer to over here, but there are hydrogen ions over there too. Oh, how did they get over there, you're wondering, right? How did they get over there? Hang on, I'll tell you a story. Because there's going to be like a little hydrogen ion slide over here. It's going to let them over there. It's the same ones over here, okay? But they're going to go from here, take a long route over there. But they're over here too. So these hydrogen ions are attracted to the electrons, okay? So the electrical force there attracts them, and then as the electron goes over there, hydrogen ion just kind of follows it. It's like magnets, just kind of pulls those hydrogen ions. Like this. But the electron is going there, but it doesn't capture those electrons. Hey, I wanted to capture those electrons, but that's not going to happen because those electrons are too high energy, okay? Okay, so they're doing this. So what's the point there? The point is here you took 2 more hydrogen ions over there, right? Okay, so what did you accomplish so far? You said nothing, right? No. These hydrogen ions are critical. They're going to generate energy. We'll see. Okay, so you see what happens. Okay. Electron goes over there, and these protein carriers carry these electrons, and just like a magnet, they pull them hydrogen ions and put them over here. It's like you put all the hydrogen ions over there. Okay? So now you have lots of hydrogen ions over here. Let me show you here. Look at all the now you can see even in this picture that there are more hydrogen ions below than on top, and look at those hydrogen ions just coming in there. Whoa, like that. See that? Just dragging them hydrogen ions on this side and putting them over there. Okay, now look, I told you they're going over here, right? They're all kind of going over there. It's like a gate over here or something. We'll talk about that, right? It's like we're attracted to that side. So that's what's happening here. The electrons bringing all the hydrogen ions on this side. Now, remember I said the photosystem 1, lightning strikes again. Same thing happens. Electrons get excited. Then you give them energy again. Okay. So now, those are excited electrons. Same thing happens. But this time, so what did we accomplish going from there to there? You said nothing. We just got hydrogen ions over here, right? Yeah, that's actually very important. So those electrons, the energy that you captured in the electron over here was used to get the hydrogen ions over here, right? Okay, good. Hang in there. So, and then during this process, the electrons that they had gained the energy, they lost the energy, okay? And then their same thing. Those electrons had gone to the chlorophyll molecule. The chlorophyll molecules love it. The light strikes again into them, and then those electrons get energized again. So there we go again. So they go up over here. But this time something different happens. This time those electrons go to produce this high energy molecule. Ta-da. See? Now they are ready to be used for whatever reaction that you want them to use it. It's right there. Okay? So now we made this cache. NADPH is like ATP. It's cache. Okay? Now, what did we accomplish in this first part? We accomplished making lots of hydrogen ions over here, which are going to be very useful shortly. And we accomplished making some NADPH. You know, that's the last of the sunlight we're going to see. That's it. The sunlight is used in photosynthesis to do what you see in front of you right there. Okay, it's used to create that hydrogen ions, and it's used to create those NADPH molecules which have high energy electrons in them. So you store them high energy right there. Okay. All right. Now, but then see all all those hydrogen ions that you created over here are used to make ATP. How's that, you say? Like this. There is this protein over here. It's a gigantic protein. It's possibly one of the most famous proteins in biochemistry. This protein is called Atp Synthase. This protein is called Atp Synthase. Okay? This protein is quite remarkable. What it does is this. See, when you make all those hydrogen ions, okay, what you do is you create what's called an electrical gradient, electrochemical gradient. Okay? Diffusion gradient. You have created a diffusion gradient. You have essentially used sunlight to create a diffusion gradient. Now, if there are boatloads of hydrogen ions over here, and there are not as many over here, the natural tendency of the hydrogen ions is to do what? To go from this side of the membrane to go that side of the membrane. But ions can't just do that. They have to have protein molecules. They have to. Ions, remember, ions cannot go to the membrane by themselves. They need carriers, like over here. This hydrogen was brought over here, or they need carriers. The big, huge, famous celebrity protein of biochemistry, Atp Synthase, is a channel for these hydrogen ions. But it's something else. Okay, as the hydrogen ions go through this Atp Synthase, they change it a little bit. They change. Every time one goes through it, it kind of like a clock. It changes a little bit, like that. Okay, and those conformational changes, change in the shape of ATP, is used to force ADP and a phosphate group. These are the precursors of ATP, and to convert them to ATP. Okay, so this hydrogen ion gradient that's created in the first part of this process is used to make ATP by this famous protein channel, Atp Synthase. And this is quite an intriguing thing, you'll see. So here's Atp Synthase in action. Here it is. Okay, here let's go through here, it's kind of cool. So here's, remember, this is Atp Synthase right there, huge, gigantic transmembrane protein. And if you look at this, those little shiny dots that you see in Atp Synthase over there in the membrane, those are hydrogen ions. They attach over there and they go to the other side. But every time they attach there, okay, they change the shape of it, Atp Synthase, a little bit. Okay, so look, here's hydrogen coming. It comes there. Okay, and it goes over there. It's coming from there. Watch this, and it's going to go on the other side of the membrane. Okay. Now, but when that happens, it changes the shape of this part of the protein because of electrical changes that occur. You know, ions, hydrogen ions coming in, they change a little bit. But that change is reflected by like a rotation, like a twisting of the protein, like that. So the fact that hydrogen come in, they twist that part of the protein. Okay, a simple ionic addition can cause a conformational change or shape change in the protein, and that's what happens over here. And that shape basically is like a twisting of that part. Okay, and then hydrogen ion is released. Now, if you look at the middle picture over here, you can see the hydrogen ion coming and going on this side and changing the shape, which is like a twisting shape of the hydrogen of the protein. Now, this part over here, this part of Atp Synthase, okay. Now, to make ATP, you have to take the ingredients, which is the ADP, adenosine diphosphate, and a phosphate group, and force them together. It's like force them together. Now, sometimes chemical reactions don't occur because they just need a little bit of energy to cause that reaction to occur. Okay, it's called activation energy from chemistry, if you recall. So if you take ADP and you have to force the phosphate group to attach to it, and it's a physical maneuver. Okay, so you take the ingredients, which is ADP and the phosphate group, and you just force them like two magnets that don't want to come together, and then you force them and you attach them and to make the ATP molecule. So this plus this equals ATP. And the reason this happens, these two molecules, they'll never together voluntarily come together to make ATP. The reason that it happens, although phosphate group has a high energy electron, this phosphate group has high energy, but it never goes attached to itself. It needs help. and they're physically brought together to make ATP. And that's why this hydrogen ion gradient is so important. So it's like this. Watch. This is ADP and this is phosphate. ADP and phosphate. Okay. First they attach to this big, huge, famous protein. Okay. Look. Now go here. Here they attach to it. Now the change in the shape forces them to come together. The change in that shape forces them to come together. Okay. Now that is cool. So that hydrogen ion gradient is used to force together those ADP and ATP molecules to make ATP. That's happening over here. See? ATP, ADP, ATP. Now, this process looks complicated in the beginning, but if you understand this, it's actually not that bad. Over here, light is coming, releasing those electrons, water donating the electrons back, electrons attracting the hydrogen ions, bringing them to this side. Lots of hydrogen ions over here, and they use this famous protein channel to make ATP from ADP and phosphate group, which ordinarily would not come together, but they're brought together. Now this phosphate group is a high energy group. That electron, the phosphorus, is a high energy electron, but it would not volitionally, but by itself, come and join ADP. They need to be physically brought together, and that's what ATP synthase does. A very curiously interesting molecule. Somebody won the Nobel Prize for this 1997, I think, for this work. This is the reaction converting ADP and phosphate group to ATP. This you gotta know. So the process is quite complicated. I just want to suggest you. All right. Now look, this process, that's where this phosphate high energy, this is created as a result of hydrogen ion going through like that. So now this is photosystem 2, photosystem 1. Light strikes the system twice. This is the world famous ATP synthase membrane. This is the big picture, the first part of photosynthesis. Now that's the light reactions. This is it. The rest of this, now the ATP that's produced and NADPH that's produced, it's used for energy in the cell. So these are the two molecules that are made from the light reaction. They can be used for anything that the cell wants to do with them, because they have high energy bonds, high energy electrons in them. And some of it, however, is saved, so to speak, for later use in the bank. And that's the Calvin cycle. That's this part. The first part of the reaction of photosynthesis occurs on the membranes, the thylakoid membranes. That's the light-dependent reactions. The second part occurs in the stroma of the cell. That's called the Calvin cycle, and that we shall talk about, inshallah, next time. Until then, as-salatu was-salamu ala rasulillah, alhamdulillah rabbil alameen, assalamu alaikum.